Hi, it's time for another math easy solution. To discuss further into Tengri 137 and now look at Odin's Triple Horn, which involves some perfect squares and whatnot. It's pretty interesting, so yeah, buckle up. It's going to be a pretty wild video. And also useful tip, if I'm going too fast or too slow, you can play this video at a different speed. Yeah, so now let's just jump right in. So before I go into it, let's just explain what Tengri 137 is. It's just the name of an online cryptic series of puzzles and riddles that some are saying is mathematical proof of aliens or advanced intelligence making contact with humans. You can learn more by watching the following video from the Outer Dark. Here's the Odin's Triple Horn. Yeah, so check that video out. So I'm not going to go into too much detail explaining what Tengri 137 is, but I was very interested in some of the mathematical calculations that was brought up, which made quite fascinating biblical references. So yeah, I might go over those in later videos. So we'll look closer into those references to see what I can find out, and we'll let you know if I find anything. Also, make sure to watch my earlier video on the magic cubes of the Tengri 137. So check it out. I made my own magic cubes calculator, and it's recall it's not actually magic, the cubes that we're using Tengri 137. So check that video out. So now let's jump into Odin's Triple Horn. So the Tengri 137 cryptic documents are translated by researchers or are shown on this website. You can go to tengri137.wikia.com, and there's translations here of these cryptic documents. So I'm going to skip through to the one that was talking about the Odin's Triple Horn. So it states these numbers, once translated, it says these numbers should make you think about our origin. A complete series without gaps. Yeah, between the numbers, perfect arranged number groups to 6 squares, check them in every direction and in all combinations. You will see that we do not lie. Then there's a photo of Odin's Triple Horn. I'll get to that in a bit. But that's not all. Our ultimate proof is more powerful. No human can place this calculation where is it now? No human can plan a calculation like this over 1,000 years before. This proof will let no questions about our existence. We want to give you an important message. Now listen, and yeah, I'm not sure which one they're referencing on that, but the initial part, as you can see, they're pretty much hyping up this Odin's Triple Horn, saying that yeah, you could sum up everything in all the numbers in every direction, etc., and it's without gaps, and I will explain that. So I'll just jump there right here. So here's that translation, and the text is translated into English there. So what you have is 4 squares that they all add up to 666 when you do it. And I mean, not 4 squares, there's 6 squares, 1, 2, 3, 4, 5, 6. So, and also here's some user commentated on that Tengri 137 website. So important information. Wow, Odin's Triple Horn with 6 magic squares, 4th order with the sum of exact 666. All of this magic squares are perfect squares. Not only the x, y, z axis are 666. 4 nearby numbers have also the sum of 666. Example here, then add those 666, etc., and then a bunch of these 666. Not only one square is perfect, all squares are perfect like this. The numbers are in complete series without gaps. So as in, you can add up every single one. I mean, it's all in order, all these numbers. There isn't any repeated, and there's no jumps in it. And I'll explain that in a bit when I go over the Excel sheet. So this guy states, this is definitely not a work of an ordinary being or standalone man. This is hype. This is some good hype. Should hire this guy. So here's a link to the high definition image. You have it here. There's Odin's Triple Horn. And now just some history on Odin's horn. The Triple Horn of Odin. Here's from this website. Yeah, this website here, symboldictionary.net. And so this is how it looks like, Odin's Triple Horn. The Triple Horn of Odin is a stylized emblem of the Norse God Odin. This symbol consists of 3 interlocked drinking horns. So yeah, they drink out of these horns. There's one there, and then there's the 2. One across here and one in the middle. And is commonly worn or displayed as a sign of commitment to the modern Asadro faith. The horns figure in the mythological stories of Odin and are recalled in traditional Norse toasting rituals. Most stories involve the god's quest for the Odin, a magical mead. I think this is a honey brewed alcoholic beverage or some sort, brewed from the blood of the wise god Kaiviser. Yeah, I don't know what's that all about. So yeah, just let me know if you know anything about that. Comment below or do your own research on it. So let's first do some research on just what magic squares are instead of just jumping in and saying, oh, it's crazy magic. So if you go to Wikipedia, here's magic squares in recreational mathematics. This is pretty cool. So a magic square is a n by n square where n is the number of cells on each side filled with distinct positive integers in the range 1, 2, etc. all the way to n squared. Yeah, such that each cell contains a different integer and the sum, yeah, so it's all different integers inside, and the sum of the integers in each row, column, and diagonal is equal. So that's just a magic square. The sum is called the magic constant or magic sum of the magic square. A square grid with n cells on each side is said to have order n. So here's a 3 by 3 magic square. As you can see here, this is 1, 2, 3 all the way to 9. The columns and rows and the diagonals all add up to 15 here. So the smallest and unique up to rotation reflection non-trivial case of a magic square measuring 3 by 3, that's this one. This one's the smallest type of magic square. So sometimes the rules for magic squares are relaxed so that only the rows and columns, but not necessarily the diagonal sum to the magic constant. This is usually called a semi-magic square. So let's go further, and I want to look at what this pan-diagonal magic square is. So a pan-diagonal magic square or pan-magic square, also called diabolic square. that's quite a good reference. It's probably where they got the reference from to get the 666, etc. So diabolical square or diabolical magic square is a magic square with additional property that the broken diagonals, the diagonals that wrap around the edges of the squares, also add up to the magic constant. And yeah, I might get into this in a bit, so just stay tuned. So a pan-diagonal magic square remains pan-diagonally magic not only under rotation or reflection, but also if a row or column is moved from one side of the square to the opposite side. As such, an n times n pan-diagonal magic square can be regarded as having n times n squared orientations. See, I'm not going to go over what all that means. Wikipedia is just the worst at explaining. So 4 by 4 pan magic squares. This is going to be relevant to the Odin's Triple Horn. So the smallest non-trivial pan-diagonal magic square consists of the numbers. Numbers are 4 by 4 squares. So these are the smallest non-trivial pan-diagonal magic squares. So yeah, here is the smallest one here. This is case A. There's actually 3 distinct versions of this. This is one. It adds. There's 16 here. They all add up to 34, and then it goes on. Thus, of 86 possible sums, you can sum up diagonal. You can do I think this plus, let's see, this would also add up to 34, and likewise this plus this, and I'll explain this all in a bit. Add up 34, 52 of them form regular patterns compared with 10 for an ordinary 4 by 4 magic square. There are only 3 distinct 4 by 4 pan-diagonal magic squares, namely A above and the following, here and here. So there's only 3 that are distinct. So yeah, when that guy was commenting above saying, oh, these crazy magic squares, they all add up 666, they can all stem from these 3 distinct pan-diagonal magic squares just by doing matrix multiplication, addition, etc. to just manipulate this. So yeah, in 4 by 4 pan magic squares, the magic constant is 34, and they all fulfill the further requirement of a 4 by 4 most perfect magic square. So here's a good illustration. Here's a semi-magic square, just the rows and columns. Here's an ordinary magic square. You have the diagonal, and then you have the pan magic. Includes this, yeah, I think this is the wraparound. So you go like this, and then here, and then this one here wraps around like that, and also you have this diagonal wrap around like that, and then you have the mirror image on this side. So that's pan magic. A complete magic square includes the corners here, and then you have this, and then you have all these little squares, etc. All add up to the magic constant. And then a most perfect square, this is actually what the Odin's triangle is pretty cool. So it has all, Odin's triple horn or whatever. Yeah, so a most perfect square includes these right here, this, and then this, and this. And basically this is an Euler diagram of requirements of some types of 4x4 magic squares. Cells of the same color sum to the magic constant. Yeah, that, as I just explained there. So in 4x4 most perfect squares, any two cells that are two cells diagonally apart, including wraparound, sum to half the magic constant. In other words, so any two cells that are two cells diagonally. So if we look at, let's say this one, actually no, let's draw it over here. So if we have this, because this one's not drawn on there, let's draw this. So if you have a square here, so let's say that's A, and then basically let's say at two cells diagonally, so you go 1, 2, this is B. So that means that A plus B equals to the magic number, I'll call that M, divided by 2. And then basically what this says now is hence any two such pairs also sum up to the magic constant. So if you added, let's say we have C here and D here. So this is 1, 2 distance across. Then what we must have for most perfect is A plus B plus C plus D all equals to, well, the magic constant M, like that. And this is actually the case for the Odin Triple Horn. So now let's explore the Tengri Odin's Triple Horn with an Excel spreadsheet that I created. You can download in the video description, as well as these notes as well in the video description. So if you check it out here, so I've made it here. I just took a screenshot of that image, put it there. Sum up all the numbers. There's going to be, well, there's 6 squares. All these are 4x4, so you have 4 times 4 times 6, that's 96 total numbers. Now here what I did was I just put all these into onto the Excel so I can actually use the numbers. So made a little figure like this. This is I call this this square number 1, this one number 2, this one number 3, and then number 4, number 5, number 6, and I'll use these as references. And now if you take all the numbers and then you sum up from smallest to largest, you go from 119, and there's 0 skips. So you go down there, it doesn't skip at all, and it goes all the way to here. Now here what I've done is I've taken each of these squares, and here's the position. I call this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, just for reference. Now if you look at each of these squares, here's I have 44 calculations, but I believe there's like 86 total, but I think those are just like mirror images or some sort of similar stuff. But regardless, this shows that they all add up to 666. So this one here sums up this bottom. This is the diagonal like cross, this one is the rows, and then if you go here, this one's a square one, so as reference above. So I just put it in here. And this one is like that. See what this one is, it's over there. See what these do. This one is that wraparound I was telling about. So they all add up to 666, which is pretty cool. This one again, wraparound. Let's see what the other ones were. Like this, yes, you have, I'll go with this one first. Yes, you have like this, if you have something like this, and then this is 2 cells across, that adds up to half. You can even see 131 plus 202, that's 333. And then 15, and then add these up together, you get 666. Same thing here. Which one's this? Let's see. Yeah, see here. This one is 2 diagonal across. This one's 2 diagonal across. So this is actually a most perfect square. In fact, all of them are. So I copy and pasted, did the same calculations. Same thing here. Square 3, square 4, square 5, square 6. All of these sum up to 666. Let's go here. So from the Excel sheet, it is clear that the 6 mathematical squares in Odin's Triple Horn are indeed most perfect magic squares, in that all 44, it's actually, I think it's supposed to be 86. I just read that after, there's probably more. Add up to 666. Hashtag wow. So it is pretty cool. So what's even cooler is that all the numbers are in order without gaps, starting from 119 to 214. Yeah, but while this is some very cool mathematics, and after many hours of over-analyzing, I spent too much time over-analyzing the Odin's Triple Horn, as well as linear algebra, matrix manipulation. So yeah, because I haven't done matrix manipulation in a long time, so that's why it just took me a while to analyze this Odin's Triple Horn. So it is clear that the Odin's Horn is nothing more than just really cool matrices, and I'll go over that in a bit. Yeah, but basically to fully understand the Odin's Horn, yeah, fix that up. So Odin's Horn, okay. Yeah, matrices calculations. Make sure to read up on matrices, as well as check on the brief tutorial I made at the end of my video on Tengri magic cubes. So now let's just jump into what I've done as well. So if you go all the way, scroll all the way up here, I made a giant table. This was when I was over-analyzing. So make a giant table. Here's a square number, a square 1. Here's the position, and then what I did was include the number here of it. So for example, this one's position 1, that's over here. So that's position 1, that's over across here. And now if you go to position, this one is position 10, that's over here. Because I made this in order, but you can, let's just go here. I'll make this smallest to largest, and then smallest to largest. So yeah, here 1 2 3 4 5. There's 1 3 1 1 5 4 1 3 1 1 5 4, etc. And I did this just to see what happens, what patterns I could find. So if you go from smallest to largest, you see a pattern here. So here's the smallest to largest. 119 is in the 6th square. As you can see, this pattern is pretty cool. So what I did was, now when you look at smallest to largest, and I copied it here to see the symmetry, and then also largest to smallest, you have 666. These ones all align. So when you go from largest number to smallest, smallest to largest, the squares are all matching up, which is pretty cool. And yeah, if you go all the way down, you see that even the 4s, all of them are aligned pretty cool, and the 6s in the middle there. So let's jump in now to see what I did. So relationship between squares. So what I did was I made these smallest to largest, but also in line with these square numbers. So if I go here, smallest to largest, but now it's already aligned from the smallest to largest of each cell. So this is 1 and 1 3 1, and I have the positions across here, and I did it across here. And as you can see, there is some sort of pattern here. This is 1 2 3 4. Actually, whoops. Yeah, I'll show you the pattern in a bit, actually. So notice, so basically the pattern here is when you look at the smallest number and then you see what position they are. So you have 1 10 15 8. Number 2 isn't like that, but number 3 is 1 10 15 8, and they'll go exactly the same positions for relative size, because this is the smallest to largest. Same with 4, 1 10 15 8. Same as square 5, 1 10 15 8, etc. And so basically, notice how squares 1, 3, 4, 5 are ordered in a similar way. And also notice how squares 2 and 6 are ordered in a similar way. If you go to 2, you have 13, 11, 13, 11, 8, 2, 6, etc. These are exact same. In fact, if you look at the difference from the 2, this one all I did was subtract the 2. So if you click this one, like that. So if you subtract, that's this one, subtract by this, and likewise all across, you'll see that there is some difference here. And the difference that I saw, well, you have this pattern here. When it's ordered from the smallest to largest, you have this 4, the negative 4, 4, negative 4. This is for the square 2. For square 3, the positions are all the same, so it's zeros, and then you have these ones across. So as you can see, this cool pattern is 8, negative 8, 8, 8, 4, etc. So that's a pretty cool pattern. So notice how squares 1, 3, 4, 5 are just matrix transformations of each other, because you could just multiply it, or just add these matrices together like that using this pattern, and you'll get the exact same one. And this is, again, goes back to that smallest distinct magic squares of the 4x4, because you can manipulate these and eventually get to it. So also notice how squares 2 and 6 are matrix transformations of each other, and you can, again, if we subtract, this one's different from square 6. So if I take square 2, subtract from square 6, you'll have all these are zeros, and you'll have these across another number. So we have 16, etc., negative 16, 16, negative 16, which is pretty cool. So now let's compare square 1 and square 2. Yeah, so what I did was I took all the square 1 positions, put them aligned like this. So 1, 2, 3, 4, these are positions, and here's the values. Now if you go back to here, square 1, it's position 1, you have this one's position 13, so that's 1, 3, 5. Position 10, we have position 11. But then if we put them according to this positions, 1, 2, 3, 4, 5, 6, 7, 8, going downwards like that. So align this together. 1 goes to 13, so 1, 3, 1 is 1, 3, 5. And this one is where the 16 is going to be. Let's look at the 16. So 16 is here, goes to 4, and that's 148. So if you look at that here, 16 goes to 4, which is, yeah, this is the 4 now. Yeah, well, let me just check that again. So 16 goes to 4. Yeah. See, what I meant was the 16 here becomes 4 here, etc. And then the 152 goes to 148. And you can see that here, 152, 148. And if you keep doing that, switch all the positions, what we end up having is, well, we have this exactly going down. This is the original position, square 1. Square 2 is 1, 2, 3, 4 is like this. This is just rotated. So if we rotate square 2, we get square 1 like that, or just the positions of it. So basically, if you look at the Tengri square 2, this one's here, and then rotate it, we get this like here. So 198450 goes downwards and upwards. So 197, 184, 150, 135, like that. And then when we take the difference across here, what we end up having is, well, this minus this, we get 4, and then we get this overall pattern looks like this. So this is just another matrix transformation. So OMG, this is when I realized I was super overanalyzing everything. So OMG, square 1 is just a rotation of square 2 plus a matrix transformation. This is a matrix transformation of, rotation and matrix transformation of square 2. Same goes for square 6, and square 6 is just a transformation of square 2, as I showed above here. This is different from 6. That's 2 and 6 are related by this matrix transformation. And I'll illustrate that in all of it. So that's all the squares are just matrix transformations of each other. This means if we find one of them, then we find all of them. And in fact, it's even simpler than that. So here's the magic matrix solver that I made. And now let's look at some cool stuff here. So here's Tengri 1, square 1. Here's square 2, square 3, square 4, square 5, square 6. And what I did right here is I took the difference from square, this is from square 1. So square 2 minus square 1, we get this, so we don't see a pattern there, because again, that's rotated. If we rotate it, then do that, we'll get a pattern, etc. So now if you look at square 3, here's Tengri square 3. Again, this is subtracted from square 1, we get this pattern. We get this pattern across here, and all of these across here. So square 4 subtract by square 1, we get this 8s like that. And then we have square 5 minus, we get 4s like that. And then Tengri, the 6th one, we don't get a decent pattern, because again, that's rotated. This one's related to square 2, or better related to square 2. And now if you look at the difference from square 2, so I subtracted square 3 from square 2. You don't get a pattern, a decent one, but then you get this matrix transformation like that. Square 6 and square 2 are related, so something like that. So recall that all the squares are just matrices, matrix transformations slash rotations of each other. So we just need to find one to find them all. And note also we have 4 matrix transformations. Namely, this one here is, it looks like a guy upside down, and and I just put 1s here just for default, because that's just 8 times everything. And then now you have this guy standing up is 2, and this one across left side. This one's rotated across this side. This one is like that. That's to resemble this one. So now that we have these transformations, what we can do is now let's copy and paste those distinct squares from Wikipedia. So here's these ones, and now if you now if you throw this inside here, and here's the calculations. Here's all the 44 ones that I had before. Put them in a nice square like that, and there's a wraparound, etc. So you can see everything adds up to 34. So yeah, these are all adding up to 34. So we have our own magic perfect square. So there's nothing special about it, because we already, well, there's nothing like alien about it. That's what I mean. So now that you have this, you have it all like this. This one is just, I just kept copy and pasted this one into here. And then now what we could do is, well, this is part of the matrix transformations. If I plus 158 to all of them, because number 158 plus, you could just test out different stuff. So if I go 157, you can notice how all these change. So when you add all these together, add every single one to 157, all you're doing is doing the exact same thing, so then the magic constant remains the same. That's basically the whole idea of matrix transformations. Let's go with 60 As you can see, it's too high, so let's go to 159, too high still, and then yeah, 158. So yeah, we have our 666. Wow. We have our diabolical magic square. So now let's look at what we can do. So when we have this, and now let's compare with the Tengri square 1, Tengri square 2, all the way to Tengri square 6. And now what I'm going to do is look at the difference from the above matrix and this. So I'm going to subtract square 1, or I'm going to subtract this one from square 1. So if we look at the difference, all I'm doing is subtracting the 2 above. And then what we get is this pattern here. And then I highlighted all the negative numbers. So you can see here we have, this is just another matrix transformation. In fact, this is the easier one because of the, it's perfectly magic, so we can just modify these. And I'll explain that in a bit. So you can see all the patterns across everywhere. And this one is the horizontal like that. As you can see, this one was just a rotation. So if you rotate it back, you get these. So remember, the 6 and 2 are the rotations. Square that, rotate it across, we get our, or rotate it down, whichever way you want to rotate, etc. You can rotate this down, and then yeah, we get the same thing. So all 2 and 6 are just rotations of it. But notice the transformations here, as explained before, where when you have a number in a cell, now if you go diagonally across, 1, 2, we get, it has to add up to half the magic number. In fact, this particular cell, magic number is actually 0. M equals 0. This is just a matrix transformation where you're not doing anything to it. When you add this, all the numbers inside change, but nothing actually changes. You could even test this out. I'm just going to copy this, and let's just throw this inside here. Let's go with paste, and then let's put values across here. So values, as you can see, is all 0. So it's just a transformation. Doesn't affect the magic sum. So you can add them, nothing changes. All it changes is the numbers. So this is a cool way. You could just by this you can find out exactly the Odin's Triple Horn. So notice how we have even more transformations, and as again note here. So this is a transformation we could use. So when we have this one is negative 28, we get 28. Whoops. Let's go back here. Now if we have across here, if this one is, let's go here, B, let's call this, if this is 34, then you go twice across, 1, 2, that's negative 34. So B goes to negative B. A goes to negative A. Then if you go with G, G goes up top here, negative G, same thing here, 28, negative 28. And this is true for all of these, because remember, these are most perfect magic squares. If you go H, there's negative H. So this is all you need. It's just this magic, this matrix. So all you need, and you can get the Odin's Triple Horn, and you don't need to go through this over-analyzing. Let's go back here. This is my over-analyzing to seeing what patterns there are, etc. Just because I haven't dealt with matrices in a while. That's all you need, and you can do pretty much whatever you want. Because remember, there's only 3 distinct ones, so you're not going to get anything too crazy, because there's not a bunch of numbers you can't use. So this means that we can go from a distinct 4x4 pan magic square to any of the Tengri matrices. For example, if we have this one here, square A, let's throw square A in here, we got 3, 3, 4, 4. We add 1, 5, 8, and then what we have is here, because remember, if you look at this one is just a difference between, so if you look at this one is equal to this minus this. So that's 28, then this goes to positive 20. These are just calculations. This one's also a negative of this. And so basically all you do is look at what you want to get, so you can move these down 1 or down 28. All that does is increases this to 28. So, and that's why we want to do it. So when you do that, and then this just equals 2. So now when you add these together, so 159 minus 28, you get 131. You get this 166 plus 34, you get 200. So basically you can just use this property, so whatever you want to get, and because there's only a few distinct ones, only 3, you're going to easily get this square here. So we can easily manipulate what's inside to get exactly Tengri square. So here's Tengri square 1, all we did was add, add this matrices like that. That's our ABC matrices. And then what we get here is this number. And if you look at the difference from square 1, that's this one above here. Look at the difference, 131, 131, everything's 0. So thus we have Tengri square 1. Now that we have it, we can get everything else. So to get Tengri square 3, well, what we could do is add 8 times the matrix transformation number 1. So we put 1 here, and everything changes here. And the reason is, again, because this is to get the third one. If you look at the difference between third and 1, we have, this one's -8. It's a guy going downwards like this, etc. If you look at it, it kind of looks like a person. Let's see which one that is. That's over here, and I made a nice calculator. So this is the first one. Yeah, that's -8. But now we just 8 times that. So going up here, where's my calculator? So 8 times matrix 1. In this one I have a big giant if calculation, and I just so I can change these if you want, change the matrices. I have 4 of them above. Let's go to matrix 1. So if we add 8 times the matrix 1, we get 1, 2, 3, 208, and 6, 6, 6, 6, etc. And then if you do difference from above is the square 3 minus this one, we get, well, 0, 0. So these are the exact same thing. So now to get Tengri square 4, we add 8 times transformation number 2. Because again, if you go look at the fourth one, this is 8, and this is a guy standing upwards, and this is number 2. So 8 times that one there. 8 times 2, and let's look at what the fifth one is, so I don't need to scroll back up. The fifth one's going to be person downwards, and it's 4. Person downwards, that's the first one, and it's 4. So let's see if that was correct. So you have 4 times matrix 1, and then here you could just do this one. So 8, 2. Then here, look at the difference below, square 4. So we have square 4. This one is square 4. Everything's 6, 6, 6. There's 0 difference, exactly that. Square 5, 4, and this one, 4, 1, and then we get 0 zeros across. So as you can see, yeah, it's pretty cool. So now to obtain Tengri square 2 and 6, as well as all of them, we could have just added. Let's write. Yeah, or instead we could have just used the ABCD matrix above. So yeah, you could do that with all of them, in fact, because even the ones that are horizontal like this, again, is the same thing. If you go 38, move 2 across, -38, 18, -18. So there is the pattern that is true for all pan magic 4x4, and I believe everything else size as well. So yeah, we could have just done that, but it's not as fun as this. So we can also rotate Tengri square 1 clockwise 90 degrees. So if we rotate this one like this one across Tengri square 1, that's because if you look at this one here, square 2 is counterclockwise of square 1. So square 1 is going to be clockwise of square 2. Yeah, I believe I said that correctly. I got mixed up with all these rotations. But anyways, if you rotate the square 1 like this, move the 201 goes up top here, and then the 131 goes to here, 201 goes to there. As you can see, the 201, 131, and then everything else accordingly. Yeah, the 134 rotates across here, and then 152 goes to here, and there's our 152, 134. So we rotated everything across there, and then you copy and paste it inside this graph. And now what we get is, because as explained here, it's just a rotation and then a matrix transformation of square 2. So now we're just working backwards. So to get Tengri square 2, we add 4 times the transformation 4, because we have this one here. So difference from square 1, this is square 2 is difference from square 1 is this person standing upwards. So instead, and that's 4 times, yeah, it's dealing with 4s. But since he's standing upwards, we need to rotate this way clockwise. So we're looking at this one right here. This is the original matrix 2. Rotate this one actually to get matrix 4. So yeah, just this is some cool stuff you could do. Hopefully you got your head around that, or you can just play around with it until you get the right one. So 4, and this one, yeah, as you see, put the 4 in there, we get difference from above 0, and that's a square 2. And you could even test it out. Let's see. Oops, let's exit this and put a 2. See what happens. We get these 8. So again, we can have unlimited magic squares. Let's go with 3. Still not right. Those are 8s. Let's go with 4, like that. And there you go. Difference is 0. So that's our Tengri square 2. These are exactly the same. So we have our square 2. Now to get Tengri square 6, we add 16 times matrix transformation number 3. And that's because, well, we could just scroll up. And when we scroll up, we get, well, the difference between Tengri 6. This is a difference from square 2. So Tengri 6 is difference from square 2 by 16, and it's person on the leftwards like that. That's matrix 3. And it's 16. So let's see what the numbers were. Where is it? And so 16, whoops, what am I typing? 16 and then matrix 3. And I think we got that wrong. Oh no, actually I forgot to put that. This is to get Tengri square 6, and then this is we added 2 Tengri square 2. Move that over. 2 square 2. So to do that, we need to copy this and put that in here because we're just dealing with the rotation of square 1 like that. So paste this here and yeah, put values, and then there's 16, 3, and there's our 0, 0, 0. That's exactly it. So yeah, that's pretty cool. That's pretty it for the calculations. So now I just want to sum up. Basically, the Tengri 137 documents made it seem like the calculation was something special, but it appears that there isn't anything alien or of higher intelligence involved, unless there's some other connections you can think of. So let me know what you think in the comments, because yeah, it's just basic linear matrix manipulation and stuff. But yeah, I just wanted to go in detail because, and also give you a tutorial on this. Is pretty cool stuff on magic squares and on what was that, recreational mathematics. That's what I think the Tengri got this from. So that's one hypothesis. Tengri got from recreational mathematics. Probably a really talented mathematician doing all this, and as well as this diagonal magic squares known as diabolic square, diabolical, and then there's a 666. I don't know, he probably got ideas from that. Anyways, thanks for watching, and yeah, it's a pretty extensive video, but yeah, hopefully you followed along. It's pretty amazing. Thanks for watching, and like always, you can download these notes in the link below as well as the Excel sheet. So yeah, thanks for watching, and stay tuned for another Math Easy